There are many essential matrix operations that we'll learn in the coming lessons. One arithmetic operation that it's important to understand now, because we're going to develop a third representation of how to think about systems of equations, is this notion of matrix vector multiplication. And as you can see, it involves the product of a matrix and a vector. Now, by the way, a vector in its own right is also a matrix, though the reason we call it a vector is because it has one column. All right, it's 2 by 1. So the way that matrix vector multiplication is defined is as follows. And I'm going to go ahead and write this off to the side. Matrix multiplication of components for a two-dimensional vector, I'll just call those two-dimensional matrix A, B, C, D, and a vector that's 2 by 1, let me call this maybe F and G, is going to take place in the following way. The way this is defined is the second vector is going to consist of scalar multipliers. So F will be the first component in the vector, and it will multiply the first column in the first matrix. Okay, so it's going to be a scalar that gets applied to the vector AC. In a similar fashion, G is going to be the scalar multiplier that applies to BD, and by definition, once we multiply the scalar by the column, we add the resulting components together. So this is what this will look like. It will be F times the vector AC plus G times the vector BD. Okay, so you can think about this as landing on the first column and this as landing on the second column. And so here we'll get, if we compress this, we'll get F times A plus G times B. And in the second row, we'll get F times C plus G times D. So notice that once you add these things together, this will be one number. This will be one number. And so we'll end up with a vector that is 2 by 1. So a 2 by 2 matrix multiplied by a 2 by 1 vector will give you another 2 by 1 vector. So in this context over here, we can imagine that our value of F is 5, and our first column is the column 1, 3. So this would be 5 times 1, 3, and 6 times 2, 4. Results get added together. Again, this is just the definition of how we conduct matrix vector multiplication. We'll see that this is actually incredibly useful. So here we get 5 times 1 is 5, plus 6 times 2, that's 12. 5 plus 12 is 17. 5 times 3 is 15, 6 times 4 is 24, 15 plus 24 is 39. There's really no difference when you're working with a 3 by 3 matrix and a 3 by 1 vector, except we do this process 3 times. So -1 will multiply the first column, so this will give us -1 times the vector 1, 4, 7, 0 times the vector 2, 5, 8, and +1 times the vector 3, 6, 9. Once again, the results by definition will be added together. And so here we'll get -1 times 1, that's -1 plus 0 plus 3. -1 plus 3 is 2. -4 plus 0 plus 6. -4 plus 6 is +2. -7 plus 0 plus 9. -7 plus 9 is 2. So in this case, we get the vector 2, 2, 2. And notice that this result is also a 3 by 1. So a 3 by 3 times a 3 by 1 will produce a 3 by 1 vector, just like a 2 by 2, a 2 by 1 will produce a 2 2x1 vector. And you can imagine that for a 4x4 times a 4x1, we'd get a similar result. Now this is what we call matrix vector multiplication. In addition to having real-world applications, this will allow us to represent a system of equations in a slightly different way. So let's go ahead and see how that might work. Let's apply this to a system. So we'll just say writing a system of linear equations in the form A matrix times X vector, there's our matrix vector multiplication, equals another vector that we're going to refer to as B. And you might remember this from the previous video in which we used B to represent our constants. So we're going to think about this matrix A as containing our coefficients. So this is a coefficient matrix. This sometimes is referred to as the variable or solution vector, because those are the elements that we want to solve for, and this vector right here is the constant vector. So let's say that we have a system of equations that we want to represent. We'll just say this is going to be a 2x2 system. So let's say I have the equations 4x plus 3y equals 10 and 2x minus 7y equals 6. Now if I write this in vector form, I can see that here I can put 4x and 2x into the same vector, and I can add to that the vector containing 3y and negative 7y. So notice that what we're doing is we're kind of working backwards here. Here we skipped a step, but we could have actually shown the coefficients multiplying each of those components. So FA, FC would have been one vector, GB, GD would have been a second vector, and then we just skip to the step where the components get added together. So what I'm going to do next is I'm going to factor out an x from that vector. We can think about this as before the x multiplied the 4, 2 vector. And here I'll factor out a y and write this as the 3, negative 7 vector. Oh, and here I should have written equals 10, 6. All right, well now notice that this is a constant times a vector plus a constant times another vector. And if I work a step backwards, right, if we think about the negative 1, the 0, and the 1 here, those were the elements of the vector that was multiplying the matrix consisting of these 3 columns right here. So what I'm going to do is I'm going to sort of imagine the x and the y as sort of lifting back up into this vector, and then my 2 columns, 4, 2, and 3, negative 7, become the columns of the A matrix, and I get that equals 10, 6. So if I conduct the multiplication forward, like we did in these last 2 examples, I'll get x times the 4, 2 vector, which is this piece here, plus y times the 3, negative 7 vector, which is this piece here, equals 10, 6. And we can kind of work our way backwards to arrive at the system. But now we have a matrix that we've identified as the matrix consisting of coefficients. Here we have a vector consisting of our variables, or the solution, if you will. And then we're going to call this constant vector our vector B. And so now we've been able to rewrite a system of linear equations in this third representation as a matrix vector product.